The subatomic world is full of all sorts of unfamiliar particles, with names like quarks, which is not the sound that an Australian duck makes, to bosons, which isn't a clown particle. Each have their respective personalities and behaviors. However, one of the particles is particularly curious. This class of particles is called the neutrinos. Neutrinos are the ghosts of the subatomic world. They interact less than any of the other known particles. Even though we are constantly bombarded by them, in fact, something like 650 trillion of them are hitting you every second, it took 30 years to prove that they exist at all. So let me tell you their story. To start with, we need to go back to 1930 when they were first proposed. It turned out that there was a maddening little problem with a kind of radioactive decay called beta decay. Beta decay is when an atomic nucleus emits an electron and the nucleus changes from one element to another. This is kind of like the alchemist's dream of changing lead into gold, although the actual elements were different. At the time, the emitted electrons were called beta particles, which is where the decay got its name. The problem was that when the energy of the original nucleus was compared to the combined energy of the daughter nucleus and the electron, the books didn't balance. After the decay, energy was missing. Since one of the most dearly held ideas of physics is that energy can't be created or destroyed, the observation of the loss of energy in beta decay sends the research world into a tizzy. Lots of ideas were considered, including the possibility that perhaps in the quantum world that energy could disappear. In 1930, physicist Wolfgang Pauli came up with the idea that the reason that the energy was missing was that because there was an unobserved particle emitted in beta decay. If that was true, the unobserved particle could carry away the energy, and the mystery was explained. These particles have come to be called neutrinos. There are 4 known forces, 2 familiar ones called gravity and electromagnetism, and 2 ones that aren't familiar called the strong and weak nuclear forces. Neutrinos do not interact with the strong and electromagnetic forces. We know that because if they did, they'd be very easy to see. Neutrinos do experience the weak nuclear force and gravity. Of the 2, the weak force is the stronger of the 2 by far. For all practical purposes, neutrinos interact only via the weak nuclear force. And the weak nuclear force is aptly named. To give you a sense of how weak it is, let me give you an example. Neutrinos originate from nuclear reactions, and the biggest nuclear reactor around is the sun. The sun emits so many neutrinos that even though that is about 93 million miles away, something like 650 trillion neutrinos from the sun hit you every second. So suppose you wanted to shield yourself from that steady barrage of neutrinos. How would you do that? Well, if you took a huge block of solid lead that extended from the nearest star, and I'm not talking about the sun, I'm talking about Alpha Centauri, which is about 5 light years away, you'd be able to block something like half the neutrinos from the sun. If 5 light years of solid lead is such a poor shield, then there is no way you can stop them, even if you use the entire Earth as your protection. Most neutrinos blow right through the planet just like it's not even there. Neutrinos really don't interact very much. So how did we detect them? Since neutrinos are emitted from nuclear interactions, one early idea was to put a neutrino detector near a nuclear detonation. However, that idea was quickly nixed as being, well, unnecessarily dramatic, so no bomb. Instead, in 1955, physicists put a neutrino detector near a nuclear power plant and basically turned the plant on and off. On, and the detector saw more neutrinos, off, and it saw less. On and off, on and off. That's essentially all it took. In the last half century and more, neutrinos have been studied in great detail. There's no longer any question of their existence. We have observed them from many nuclear reactors and can even generate beams of them and shoot them hundreds of miles through the Earth to distant detectors. We have seen neutrinos that were created in distant supernovae. We have even observed neutrinos emitted from the radioactive material inside the Earth. Neutrinos are now familiar denizens of the particle world. Now, this doesn't mean that just because we've studied them in great detail, that neutrinos have told us all of their secrets. Neutrinos are unique in the subatomic realm in that they can actually change their identity. In another video, I'll tell you about this totally crazy behavior.